Resuming with the session. So we have Dr. Sumantra Dutta Roy with his presentation.
Okay, I just thank the organizers once again for having faith in me and please forgive me because this is not really a very well structured talk, and although this is a workshop on deep learning, I am learning the subject myself and I'm a pretty disorganized teacher. And some of these will be through slides, there'll be some videos, there'll be some horribly handwritten documents. So it'll be a little bit of a avial or a khichdi or a smorgasbord of all of this. So please bear with me. And plus also the fact that thanks Sanodia sir for allowing me to try to cover something very basic, because it was a bit more natural also for me because I'm also learning the subject myself. And as has been described before, I'm a complete fraud. Okay, in that I've been desperately trying to masquerade as an electrical engineer for a very long time. I'm a computer scientist by training, but now I've ended up as being neither. Okay, so we'll start the story on neural networks. I'll try to cover some portions, so please forgive me in case I get too basic. And if you're a practitioner of this field, you know much more about this field than I do. And here, basically, I'll just try to cover some very basic components, some of which will typically not be there in textbooks, but I found it useful to understand the topic myself. There'll be a bit of history, there'll be a bit of fun, bit of intuition. So the story actually starts with a perceptron. A perceptron, as we know it, it's a linear classifier. Now, what do we mean by this? I'll just start from very basic high school mathematics. From high school mathematics, so if I've got two independent variables, let me put them on two axes, x1 and x2. So my space is two-dimensional. Now, if I have an entity which partitions the space into two parts, or very strictly speaking, three parts, the third part which has measure 0. So in this case, one of the things is the curve which is doing the partitioning, or the hyper surface which is doing the partitioning, is always one dimension less than the dimensionality of the space. I think this is something which has to be relatively intuitive. So for a two-dimensional space, the curve which is doing it, I've taken the simplest possible curve, that's a line. So it will have its equation in the form. So if I had variables, if I had, let's say, the equation of a line y equal to mx plus c, then if I write that as a function of x is mx plus c, okay, so that becomes a function of x. This is in its implicit form. So just as we learned in high school, that is the implicit form of the equation of a line. If my two variables are x and y, is f of x comma y equal to 0. So that gives me the equation of the line that partitions the space into two parts. In one of them, that function of the input variables will be greater than 0. In the other one, it will be less than 0. Now, that's completely immaterial. It doesn't matter whether the greater than 0 is on the top, at the bottom, to the left, to the right, or at an angle. It's just that one of them has this function to be greater than 0. It is exactly equal to 0 on this line, and it is greater than 0 on the other part. Right? So here, since we have got variables x1 and x2, and this is something that we can extend to higher order dimensions as well, this sort of notation, we'll write it like this. So basically we've got, so this is in a non-homogeneous form, that is every component here is not a function of the input variables, because there is a constant term also. So this is a non-homogeneous form. I can convert it into an equivalent homogeneous representation as well by taking another variable called x naught, which I take always to be equal to 1. Then I'll have a homogeneous representation. It just basically ekam sarv vipra bhavda vadanti. So it's just that one concept is interpreted by the wise in more than one manner. So that's completely equivalent. So as I mentioned, so this hyper plane y of x equal to 0. In this case, we have a one-dimensional entity, which is a line which is lying in 2D space. It is embedded in 2D space. Okay, and as I mentioned before, the relative location of these regions is immaterial, which is above, which is below, which is to the left, which is to the right. Now, if we look at it, although the story started off with a neural network, if we look at a non-neural interpretation, it is basically I want to find the weights such that I get a decision. All right, so I've got a non-neural network interpretation. So the input data could be d-dimensional, they could be scalars. Things like, so suppose I'm a bank manager and I want to approve an application for a loan or for a credit card. Then I'll look at some parameters. Let's say, does the person have a salary account in my bank, the years of residence and the years of service? Does the person have any outstanding debt or not? So some of these parameters would get positive weightages, and especially if a person has a previous unpaid loan or has a debt, then that should be weighed with a negative factor. So because that's going against my application for a further loan. So what I'll need to take is I'll need to, in a simplest case, I'll take a linear combination of all of these parameters, and the linear combination weighing coefficients would be positive or negative depending on what is the chance, better chance of getting a loan or a credit card or not. The output has to be plus minus 1. Should I approve the loan or not? Should I approve the credit card or not? All right. So we can pose the problem as a linear problem, a linear decision boundary. So I've taken a weighted sum of all of these parameters, D parameters. If this is greater than a threshold, then I'll approve the loan. If it is less than the threshold or less than equal to, I don't worry about too much, then I deny it. So one of the things to notice is I can put this equation in the form of this equation out here, right? W naught, or rather minus of W naught represents a threshold. So I can put it in this form. So this is the simplest way to interpret something like what this basic problem is. So some weights can be negative, and that is obviously going to have an adverse effect on one's credit rating. Now, a little bit of history. This basically started with Frank Rosenblatt. He was an engineer like most of us, and he came about with what he gave a neural connotation. He gave an architectural connotation to this decision problem for a bank manager. He said that the linear combination, the linear weights for each one of these variables, and imagine this as if it were a neural network. So the input parameters getting multiplied by the weights, and these weights are what I have to estimate. Either somebody tells me, in which case my neural network is learned, but if I want to have adaptive parameters, the way Frank Rosenblatt realized it was with a combination of potentiometric resistances and actual connections, because that was the inherent theory at that point in time. That is, if I have some sort of a electrical circuit like this, would I be able to replicate some of the connections in the human brain? So that was the idea. So this was a neural connotation, and this extra part, which involves the comparison with a threshold, that can be modeled with what is also called a bias in neural network terminology. So I can look at this, I can look up this computational node as something that sums up all of these inputs which are modulated by these weights. And what I have here in this little animation is I've got what in neural network terminology is called an activation function. This could be linear, this could be non-linear. In the simplest case, it could be a unit function. That is, it's simply adding them up and pushing them out. But if I have to take a decision, I'll need a non-linear unit. So non-linearity is something that is acceptable. So Frank Rosenblatt's perceptron was a single layer neural network with a signum activation function. Signum is -1 or +1, right? And typically mathematicians don't like functions with
See, it's still continuous, but it's not differentiable. It's not differentiable at x equal to 0. The input parameter equal to 0, and mathematicians don't like it. But we engineers always want to have a way out. We'll say that we'll approximate it by something like a hyperbolic tangent. Okay? Because I can make that slope as steep as possible, and I'll still have a function which is continuous, which is differentiable. In fact, it's got derivatives of all possible orders, and it'll have some very nice properties. Why? Because as an engineer, I've got a selfish motivation in doing optimization. Whenever I want to do an optimization, I'll have to take partial derivatives. So I know that I want to differentiate it. All right? But when Frank Rosenblatt proposed it, he proposed it in this form. In fact, his classifier was a -1 + 1 notation, which is pretty interesting because about 3 decades later, when the support vector machine theory came about, that also used the same ±1 notation. It's actually pretty useful. We'll see some uses. So if this activation, if this linear combination, or in this case, it's a simple multiplication of the inputs with the weights and a sum up. If this turns out to be greater than 0, then let's have the activation as +1. If this turns out to be minus, we'll have activation of -1. Like if I'm the bank manager, I'm denying this loan because this person's debts are possibly beyond that allowable threshold. So y of I, that's the output. This is a function of the inputs. I can also write it as a function of the inputs and a function of some parameters. These linear combination parameters now have an architectural connotation in a neural network, which are the weights of these connections. So I can write this in a non-homogeneous notation as W transpose Xi plus B, or in a homogeneous notation by taking one more extra variable, which I call X0, which is always 1. My only intention is that I don't want to give a step parently interpretation to this. So I also multiply it by a dummy variable and I take it inside. So obviously my weight is 1 more dimension. That is just mathematical convenience. So what is the learning problem? So this is called bias. The learning problem is to find these weighting parameters. I've got homogeneous, I've got a non-homogeneous. The learning problem is to learn these weights from a set of representative examples. Okay, knowing full well that some of these weights could be negative, like outstanding debt, which is an adverse effect on my credit rating. So a little bit of history. So this is Frank Rosenblatt. He was an engineer like most of us, and in fact his life was filled with tragedies. He had some of the first working neural networks. In fact, one of his systems, nowadays we've got mobile phones with scanners, that is visual sensors in them. That time it was just a couple of photo detectors, light dependent resistors, an array of them. You had to shine whatever you wanted to be imaged very brightly at them, and every one of these would respond. So one of the things that Frank Rosenblatt actually showed was that if the 10 numerals were displayed to his system with a simple perceptron, he could learn to differentiate between the 10 numerals. So he basically had a 10 class classifier and a perfectly linear classifier. That time Rosenblatt didn't know about it, but today we know that whatever he tried to do was a simple linear classifier called a perceptron. He was also up against one of the doyens of that period, Marvin Minsky, who's also known as one of the founding fathers of the field of AI. By the way, there's some other interesting things as well. Marvin Minsky was a student of a Canadian researcher named Tucker. So if you have studied support vector machines, the KKT conditions, Karush was a master's student in Chicago whose master's thesis in 1939 was found out some 40 years later. And Kuhn and Tucker, so A.W. Tucker was the Canadian researcher and Marvin Minsky was actually one of his students. So there's a very nice thread of AI and machine learning out there. Now, he was up against Marvin Minsky. One of the things Marvin Minsky accidentally found was that even a very simple problem like the XOR problem could not be solved using Frank Rosenblatt's perceptron. So all of Rosenblatt's intuitions, all of that suddenly went down the drain. And in fact, one of the biggest tragedies is that he passed away at the young age of 41. He passed away on his birthday in a boating accident. Okay, it's complete tragedy. And it's only nowadays that people are giving him credit for the engineering aspect to neural networks. In fact, some of the ideas of deep neural networks also follow from some of his concepts, and I'll come to some of those ideas. So this is Rosenblatt's very sad story. And I give you an example of one of the real working systems. So what is this XOR problem? Today we know that the XOR problem is nonlinear, but Rosenblatt didn't know it. And in fact, one of Marvin Minsky at that point in time, he had challenged people to, now we know that just put one more hidden layer and it's possible to solve the XOR problem. So what is the XOR problem? The XOR problem is a very simple one. So if I've got two independent Boolean variables. So in this, so these Boolean variables, Boolean input variables can take on values 0 and 1. So I've got 4 points here, right? So the XOR function for two input variables is 1, which is 1. When exactly one of the inputs is 1, the rest is 0. The two inputs are the same, then output would be 0. So XNOR is obviously a complement of that. So the idea here is, so these X's indicate the points in this little animation, they indicate the points where this output function would be 1 and the circles would indicate where it's 0. Now, one of the things that's clear is that the 1 and the 0 outputs, they are separable, right? Because I can always have a curve. It's a two-dimensional space, a curve is a one-dimensional entity, I can always have a curve which separates them. But the problem is this curve is not linear. Okay, that is the problem. And Rosenblatt's classifier was a linear classifier. So there's no way on earth I can have a line which separates the 0 class from the 1 class. So this is the XOR problem. It's not that there are no solutions. There are many solutions, and possibly what I'll do through the course of my talk today is I'll try to find some of them ad hoc. So it turns out that there is no one way to solve the XOR problem. In fact, I'll try to cover about 4 techniques to do so, which will also give us some design techniques to design neural networks for a particular problem. But there's also this is nonlinear, perfectly fine. Because now at least intuitively we know that I can add more layers. Okay. But there are still some unsolved problems in neural networks and in deep learning. How many layers, right? How many neurons? So it's something which is a bit like this. If you watch this famous Ramesh Sippy movie, remember which this is? This is Sholay. Yeah, this is that famous scene. Kitne aadmi the? All right, so here Gabbar Singh is asking how many people were there. So this is in fact the question which is not easily answerable. That is, how many neurons do you need, and also how many layers? Okay. See, with experience one can come up with some answers, but the trouble here is there is no algorithmic way to get a particular solution. Now, this may sound a bit odd. In fact, while teaching this, a lot of us are teachers here. These are some of the questions that come up to us from the class. How do I decide on how? See, I can still decide on the number of inputs. I can decide on the number of outputs. But I can't decide on, okay, suppose even somebody's told me, take one hidden layer. There is no algorithmic technique which will tell me how many neurons I'll put in that hidden layer. More or less, What do I do with them? Same dimensionality as the input? Because I can have a workable solution, in fact, even to this XOR problem by more than one way. That is the thing. So, itne aadmi the, when Gabbar Singh asks this question, how many people there were? This question is equally applicable to a neural network. In fact, in electrical engineering and computer science, this is not really unheard of. Look at sequential circuit design. There's an algorithmic way to do so. I pick a flip-flop, I take its excitation table, I write the state machine, I write the excitation table for the state machine, and I've got an algorithmic way. I can design a sequential circuit with a computer program, with an algorithm. I cannot do it for an asynchronous digital circuit. Remember, the only asynchronous circuit which possibly can be designed very easily is a ripple counter. It's no accident that textbooks on digital logic don't have anything more than a ripple counter, because that's the only thing which one can design, and that too, one designs asynchronous circuits with experience. So there is no algorithmic way which tells us do this, which one can do for sequential circuits. So this problem is pretty similar. Okay, there are theorems which say that there exists a neural network which can solve this problem if, let's say, there's some things to do with the VC dimension. But there is no algorithmic technique to help us arrive at one particular solution. That's a big problem. Nowadays, people are talking in terms of deep learning. It actually started the importance of deep learning, wherein a little bit of experience would be necessary, and the fact that we are willing to tolerate some amount of uncertainty in what we are doing, that okay, maybe this will work, or because this works, there's a good chance that there might be some sound theory behind it, although today we may not have a good hold on that. So the 2018 Turing Award went to these three people: Sergey Bengio, Jeff Hinton, and this gentleman, Jan LeCun. In fact, if you remember a little bit of the history of that particular point in time, while Bengio was looking at applications, Hinton was trying to develop some bit of theory. Look at Jan LeCun. So this is the 1990s, which is somehow the peak period of traditional machine learning, because one of the biggest success stories today in machine learning, which almost every person knows about, is, what is it? It's there in even an entry-level mobile phone. The Viola-Jones face detector. Okay, the theory for that, which is actually based on an ensemble called AdaBoost. Okay, the AdaBoost learning algorithm whose coefficients are small enough to be embedded in a small mobile phone with very limited compute power. So the Viola-Jones face detector came about in the year 2000. 2001, they had that journal paper version of that. In ICCV 2000 or CVPR, all of these two around this period. So this is the peak period in traditional machine learning, statistical machine learning. For every success story in traditional machine learning, Jan LeCun challenged the community and said that I'll have a neural implementation of this and I'll do at least as well as you can. So if you look at Jan LeCun's publications, he had a face detector almost immediately after this, wherein he beat the performance of the Viola-Jones face detector. But the Viola-Jones face detector, the beauty is also in its simplicity. Okay, and in fact, a set of heuristics, an integral image representation, then the hierarchy of feature detectors, and of course AdaBoost. AdaBoost is the basic philosophy is pretty interesting. So if I've got something which is one of my limitations, I should try to work on top of those limitations to try to lessen them to become a better individual. So it's got a very beautiful philosophy. Then also another very nice heuristic which was used in the Viola-Jones face detector is that I'll use the computationally light feature detectors on more pixels. I'll use them to prune out my search space for faces. So a bit more complex feature detector, I'll use it on a smaller number of pixels. A bit more complex one, I'll use it on an even smaller. So things like very simple Haar light detectors. So if I look at a face, the forehead and this part would have an obvious difference in average intensities. Or let's say the bridge of the nose with these two eyes. So it was a beautiful collection of heuristics in addition to some sound statistical machine learning, adaptive boosting. But Jan LeCun had these systems, and also to do with, I heard the right answer here in terms of OCR. So in fact, Jan LeCun had a couple of optical character recognition systems which could beat statistical machine learning based optical recognition systems by a large margin. So for every advanced in statistical machine learning, Jan LeCun had a neural implementation. And in the course of one of these, came about in 1992, the first deep learning architecture, what he called LeNet. So Le, it was actually a bad pun on the first part of his last name, as well as La means the in French. So LeNet meant the network. Okay, so we'll come to a little bit of history, we'll see where that comes about, and we'll see some nice stories and some interesting theory to do with that. First, let's look at what Rosenblatt wanted in terms of the perceptron learning criterion. And the interesting thing is this is also related to the support vector machine theory a little bit. So the simplest perceptron is a linear two-class classifier wherein we are given the ith training point and the target output is plus minus 1. The way Rosenblatt posed the problem was with two classes being plus or minus 1. You'll note that the support vector machine theory also has two classes being called plus and minus 1. So if you're using, let's say, something like SVM Lite or some library, you use an SVM, you'll have to call one class as plus 1, the other is minus 1. If you call one of them as 0, the other as 1, it won't work. That's because this theory, it's also an elegant way to solve the problem, just so that the mathematics becomes even more elegant. That's why they used it. So this is the idea. So there is an activation function which was the signum function for the perceptron. So it would be, that is, we declare it to be class C1, that is plus 1, if this is greater than or equal to 0. And we declare it to be the other class if this is less than 0. So here you will see the elegance of Frank Rosenblatt's formulation. And for that matter, even the SVM, the first hard margin SVM formulation of that gentleman, the lady, and I'm becoming senile, I've forgotten. Vladimir Vapnik, right? Vladimir Vapnik. So if I combine the two, I can say that I get correct classification if Ti into this is greater than or equal to 0. So instead of writing two inequations, I'll just write one equation. Okay, so this formulation is elegant. Now, the way that Frank Rosenblatt had posed the optimization problem, this is only one out of an infinite number of possibilities. He used a very simple one, which is typically called, nowadays it's called the perceptron criterion. If there is correct classification, my penalty is 0. If it is wrong, then I take the penalty and I take the sum of all of the penalties. So this is a simple criterion. That is, I look at all of these, I sum them up, and I put a negative sign here. That's it. Okay, that's what I want to do. See, you might say that today that is not a very good thing to do because there is no penalty for how much misclassification is. So if you have learned SVMs, you know that how much the point is misclassified, it's also a penalty. So if you remember the SVM diagram, what is it like? It's like we've got our own country, we've got our friendly Western neighboring country, and in between we've got the what is that called? Line of control, and there's a no man's land in between. So that no man's land is the margin, essentially, twice the margin. What is the SVM criterion? If a point is in India, then we don't penalize that point. If the point goes inside no man's land, we still don't penalize it. But if it crosses the decision boundary in the no man's land, if it crosses the LOC, we penalize it slightly. But if it goes out, then we penalize it even more. Okay, so that is a bit more natural. But Rosenblatt did not use that. He had this very simple function. Actually, this simple function also works. Rosenblatt solved it numerically. we'll all note that it's actually not a very easy problem to solve. Okay, it's actually a very difficult numerical problem to optimize. And the weight update rule, which is used is Cauchy's weight update rule. There's actually a little bit of history behind the weight update rule also, we'll do that. So any form of learning today, any form of learning, even a deep neural network, let's say we use the Adam optimizer there are two very famous start points, initializations for those optimizers. So even with those, the basic premise behind them is a variant of something very simple called backpropagation. But even more fundamental than that is the iterative weight update equation, which is less than 200 years old. It's about a quarter to 200 years old today. So this is mathematician Cauchy, and in 1849, so it's as recent as that. Okay, it's not a very classical math equation. So in 1849, he came about with the weight update equation, which believe me is completely non-intuitive. This is one point where people don't really appreciate it that well in the class, and often one has confusions. So let's look at this equation. This apparently is a harmless equation. This says that if I've got a neural network with many layers, so I take all of the weights in every layer, I stack them up into one long column vector. I say that these are my weights of the neural network. I'll need to update them with each iteration. So between the tauth iteration and the tau plus 1th iteration, okay, first point, why do I need an iterative procedure? Because this is non-linear. All right. We'll even note that what is the point at which any engineering student is exposed to a nonlinear optimization problem which needs an iterative solution? The Newton-Raphson method. Okay, and it's actually very depressing to know that a quadratic equation is the highest degree equation which can be solved in closed form. And who said that? It was actually Al-Khwarizmi. Mr. Algorithm, the term algorithm is actually an anglicization of the name of this person, Al-Khwarizmi, who lived in what is current day Baghdad. He is responsible for, well, he also said why the term algorithm came about is a finite set of steps to solve a problem. So that is why it's named in his honor. And in fact, one of the treatises of Al-Khwarizmi is Al-Jabr, and the anglicization of that term today is algebra. So Al-Khwarizmi was responsible for many things like what is called the Indo-Arabic set of numerals. Before that, believe me, continental Europe used to work with the Roman numbers systems. Okay, that is taught to us in school. And that's one thing which we just want to forget. Because forget converting numbers. Calculations in Roman numerals are not easy. So Indo-Arabic numerals, then the concept of zero, all of that actually went into Europe, the Western civilization, from India through this gentleman, Al-Khwarizmi. So Al-Khwarizmi was fine. He was responsible for this. So iterations. So any higher order, higher degree equation has an iterative solution. Only in special cases can we work out closed form solutions. But in general, we'll have to go the iterative way. Now there are two other terms here which need a bit more attention. There is an eta. There are three things actually. There is a minus sign, there is an eta, and there is a gradient. Okay? All three need explanations, because if you remember the Newton-Raphson method, you'd say that there should have been a plus sign here and not a minus sign. This is something which is completely non-intuitive. But Cauchy, for all the tough theory that he introduced, he had a rather intuitive explanation also. Shockingly enough for a mathematician. Let's deal with this. First thing to check is there dimensional consistency? That's the first thing that we should try to understand given an equation. So if you have got weights across different layers, all of which we have stacked together to get one long, tall column vector, we know that at least the first and the second term have the same dimensionality. Alright, so if there are n weights, there will be a n cross 1 vector here as well. So there is dimensional consistency. The step size, we'll come to that a little bit later. The minus sign, this is the burning question. That's why this is in red. And Of course, what is this? This is a gradient. What is a gradient? A gradient is a partial derivative. So if I've got n variables, I've got n partial derivatives, the first order partial derivative. Please note that there is no second order term here. Had there been a second order term, it would have appeared as a Hessian. So this is, what is this? This involves a Jacobian. That's all first order derivatives. If I had second order derivatives, I would have had a Hessian. Right? So this is a first order approximation. It's an iterative equation anyway. So see, if I've got n weights, I'll have n partial derivatives. And what is the gradient? A gradient is collecting together all the partial derivatives, putting them in a long column vector. How many of them would I have? N cross 1 once again. So it's dimensionally consistent. So if you see the vector terms here, all three of them have dimensional consistency. The rest are scalars. The minus sign, which we have to explain, eta is the step size. We'll see what that is. So look at this little animation. So suppose I've got these two. I've just got two axes, two variables, x1 and x2. And this is my error curve. And what I want to do in the error curve is to find the minimum point, a local minimum. Okay, the bad part about all of these optimizations, typically in machine learning, is that the best that we can hope for is a local optimum. Because a global optimum is either a combinatorial problem, which either falls into the NP hard. NP hard is bad enough, at least the NP complete set of problems, or NP hard, or worse still, has infinite complexity. That is, these are these probabilistic. See, I started with a little bit of a filmy connotation. I showed you that clip from the film Sholay. So using a filmy connotation once again, I like to call it the good, the bad, and the ugly. Okay, good are problems which have polynomial time complexity. All right, so FFT, n log n, or n to the power some constant. Bad are where it is, the time complexity is a constant to the power the size of the input. Like a traveling salesman problem, traveling salesperson problem, or even in hardware. Let's say if I want to do digital design, I've got n Boolean variables. I'll at least have to calculate all the minterms. How many minterms? 2 to the power n. If I want to find all possible functions of these 2 to the power n minterms, I'll have 2 to the power 2 to the power n. That's exponential, that's bad enough. But if I want to do digital design and precise digital design, I'll have to incur this complexity, irrespective of what my colleagues from computer science tell me. Worst are the scum of the lot, the good, the bad, and the ugly. That's a Clint Eastwood film, if you've seen some old westerns. So the ugly are algorithms which are probabilistic algorithms. They'll converge with probability 1 to the optimum solution, but unfortunately, there are no time bounds for that. Okay, so what we typically do is let it run for a couple of days, which actually typically happens for most of our deep learning problems. Okay, the learning, we have to stop it at a particular point. There are heuristics, there's early stopping. We like to look at the error, the validation error vis-a-vis the training error, and the point where, let's say, overfitting is ruled out. But then sometimes that curve just rears its ugly head up like a cobra. When the error curve starts getting larger, so, okay, we'll do early stopping. So there are lots of heuristics, but that's the problem. They don't converge very well in practice. All right. So this is, we want to look for a local optimum. So suppose we choose a point for the iteration. We need a seed point. So what do? We choose this point, call it W. We take it up and we find where it cuts the curve, and we find its y coordinate. So just look at this little animation. We simply find its y point, which is E of W. Essentially the error curve. So we have essentially found the point W comma E of W on that curve. W in this case is a scalar. I've taken a very simple one-dimensional example. Now, what do I need? Remember Newton-Raphson, I need the next iteration. How do I do that? So suppose I perturb. So if I've got an independent variable, so it's like if I've got just one variable, my independent variable I always plot it on the x-axis, the dependent variable I always plot it on the y-axis. That's the function, right? So what do I do if I want to take a derivative? I perturb the independent variable and look at the perturbation in the dependent variable. That's what I do. So I change W to W plus delta W. I take it up again. I read it off the curve, so the point on the curve, and I read the value of the function there, which is E of W plus delta W. Now with these points, I have the numerical values. What I do is, I say that, well, this delta W is so small that if I join them with a line, that is approximately the curve itself. So the slope is defined as, note this very carefully, this is E of W plus delta W minus E of W divided by, so it's the change in the Y coordinates divided by the change in the X coordinates. So it's basically this. And this comes here, and if I take the limit, delta W tends to 0. This is my definition of the derivative. Now for us, for those of us who are electrical engineers, we are taught in a subject like digital signal processing that if I have a differential equation, what corresponds to it in the discrete domain, discrete time domain, is a difference equation. Nobody tells us that the minimum change in the discrete domain is 1. So that difference equation that comes here, E of, let's say, W plus 1 minus E of W, that difference equation actually comes from the definition of a derivative in the discrete domain. Nobody tells us this in school. That's the unfortunate part. So if I take the limit, it basically becomes the partial derivative. In this case, the partial derivative is the same as the complete derivative because we've got exactly one variable. So what does this mean? So if I take all of these partial derivatives, I've got n weights in my neural network, I take all these partial derivatives, I've got delta. It's like the slope. Okay, the gradient is the slope. So W vector is, I've just taken all of these weights and put them as one long column vector. So this, the gradient, is the set of all partial derivatives, and therefore it is dimensionally consistent. That's all that I wanted to say. The minus sign is interesting. See, by definition, the gradient is in this direction. It is in the upward direction. So if I want to go for the minimum, I'll have to go against the gradient. You see this? Now you might argue that why didn't we take W minus delta W on this side and take the gradient there? It doesn't matter. Either way, if we have the gradient, we need to go against the gradient. See, here we didn't make any assumption as to whether W plus delta W, whether delta W is positive or not. We normally take that as an assumption. But either way, the important part is we need to go against the gradient if I want to go to the local minimum. That is why there is a minus sign. The Newton-Raphson formula does not involve going against the gradient. Therefore, the Newton-Raphson formula is closer to the derivation of a partial derivative. And that's why you see that sign difference. We are essentially trying to do two separate things. Cauchy's idea is that I have to go against the gradient if I want to get to a local minimum. And this is interesting. So eta is a step size for that. Why is the step size important? Because if I've taken a small change in the independent variable, if I take a very small step size, I'll need a lot of iterations in order to get to that local minimum. On the other hand, if I take a very large step size, I might miss the local optimum, I might miss the local minimum altogether. Okay, which means even more iterations for me. So this is a tunable norm. And today, most numerical optimization packages, see, it's very nice to say that, oh, I've got a nonlinear optimization problem, I'll solve it using Levenberg-Marquardt. Levenberg-Marquardt, fine. I've also got adjustable gradients. There's that parameter lambda in Levenberg-Marquardt, which actually gives sort of a momentum term, which says how big should or what should be the rate of change. I can additionally, in some variants, I can give a table of how this should change, maybe according to my experience. However, let's also remember that it's not that easy. And that is why software developers such as MATLAB, they actually literally overcharge us. Their rates are rip-off, MATLAB. In fact, the cheapest versions are student packages or even educational packages. Look at their corporate deals. They essentially make their money based on this. It's not even science. It's actually a black art, numerical math. Okay, it's literally black magic. All right. So this is what I talked about. Eta is the step size, and it's also called the learning rate and a tuning parameter, which could be adapted. So this is what I said. So it's always a sort of a fight between if I take smaller steps, maybe I'll take longer to achieve the local minimum. On the other hand, if I take a large step size, I may miss the local minimum altogether. So that is where the part comes in. So I hope this part is clear, because at least takes a lot of effort to, the explanation is very easy, but sometimes takes a bit of effort to recognize why there is a minus sign, why there is, see, because any weight update equation, we will have to use this quarter to 2 centuries old result. It's as recent as that, okay, about 175 years old. Okay, now we'll try to extend, Rosenblatt's term, Rosenblatt's concept into having one more layer. And in fact, this is what actually formalizes the concept of neural networks. And it is from this point, we'll see where deep networks come in. What is the essential difference between a multi-layer perceptron and where do deep networks come in? And where has historically, some of the motivation for this, where has it come from? It's actually come from the real neural networks. Okay, many things have been inspired by real neural networks. So if you're from the electrical engineering community, you would have studied wavelets and studied optimality, time-space optimality with regard to wavelets. Is that uncertainty, something very close to Heisenberg's uncertainty principle. So there's an uncertainty for the lowest level of resolution in time and space. So if you go too much deep into time resolution, we lose frequency resolution there. So that is there. The first wavelet to come about was actually due to Gabor. 1946, Gabor was a Hungarian. See, that point in time, Hungarian mathematicians sort of ruled the science world. Who was the other famous Hungarian mathematician around 1946 who gave his models, and we swear by his models even today? Von Neumann. Every computer that we use is based on the von Neumann architecture. The Harvard architecture, well, I'm lisping. The Harvard architecture actually precedes the von Neumann architecture. Harvard architecture is 1938. What was that? Distributed. So there would be one memory for instructions, there would be one memory for data. Separate things. That came because that came about in Harvard University. Howard Aiken was the name of the computer scientist. He implemented his computer using electromechanical switching, relays, those little boxes that make that clicking sound while doing that switching. So Howard Aiken has this idea of separate memories, but von Neumann's architecture and his idea was that keep one common memory for data and instructions. Right? So that was, we swear by that Hungarian mathematician's model even today. So, sorry, coming to Gabor. What motivated Gabor's theory? See, for those of us who work in image processing and computer vision, we know that a Gabor filter is basically, what is it? It's a sinusoid modulated Gaussian. What is a Gaussian? A Gaussian is that bell-shaped curve. Okay, it's like taking a carpet and putting it on a rod, which is the median or the mode. Put that carpet and it's going to spread around in a bell-shaped manner. It's going to be a thin or tall Gaussian or a fat and flat Gaussian, like my belly. So that is what, and additionally, what happens if the carpet is like this, and let's say the pet dog or the pet cat walks in a particular direction along that carpet. The carpet gets wavy, right? It gets displaced from its position. So this is a sine wave, but it's a sine wave in a particular direction. This is essentially a Gabor filter. A Gabor filter, what Gabor showed was that this is optimal in terms of time-space, the time-space continuum. This is in fact one of the first wavelets. The interesting part was in the 1980s, there's a neuroscientist by the name of John Dogman. Okay, he found that the cat's visual cortex has some cells which actually do what a Gabor filter does. So it's again biologically motivated. Okay, the funny part is the gentleman's name was Dogman, but he worked on cats, okay, dogs and cats. It was raining cats and dogs here just a couple of days back also. So there are lots of things which are also based with ideas which have come from biology. And in fact, nothing exemplifies this better in deep neural networks concepts such as local receptive fields. It's there in the human visual cortex also. Okay, the V1, V2 cells. We've got local receptive fields. It's also, see, Mother Nature has often found out a way to be energy efficient. So with a smaller number of connections and the same amount of energy that we get from food, the neural network somehow over centuries of evolution has actually come to that. So there are lots of different concepts in deep neural networks which have been motivated from basic biology. We'll start our story with a multi-layer perceptron. So the idea here is put one more layer. Take a perceptron, put one more layer, and perhaps change the activation function. So in this case, once again, that same problem is there. We can quantify the input space. That is in our hands. The problem, how many variables it's going to have. We can have one extra variable, which is always one, which is our bias term. Remember the role of the threshold in the bank manager's problem, whether I should approve the loan or not. This is basically that weight. This is the weight of the bias. I've got another layer here, which I call the hidden layer. How many neurons is that going to have? It's only from experience. Similarly for a deep neural network. For a deep neural network, if I know that I've got, let's say, 28 cross 28 images, which was MNIST data set, 28 cross 28. So I know that if I want to have a neural network for that, 28 cross 28 is 700 something like that. So that is the size of my input. And if I know that my output is the 10 digits, so I know the neurons in my output layer. Now, what I don't know is how many hidden layers and how many neurons should I put in each hidden layer. With some experience, I know that typically a deep network starting from LeNet, 1992 onwards, starting from LeNet, I know that there is a contractive structure. It's like a carrot, okay, wide to small. So there, I know that there is going to be some form of pooling. LeNet introduced average pooling. I could have max pooling, which is much simpler computationally, right? So it's much simpler, and I'll have some subsampling after that. So it will gradually reduce in dimensions. Nowadays, it's known that the final layers would be fully connected layers. Okay, and after that, so the complexity in every neuron being connected to every other neuron would be there only towards those fully connected layers. 1, 2, 3, but not too many. That is something that we know from experience. But unfortunately, there is nothing which algorithmically tells us that Gabbar Singh question in Sholay. Itne aadmi the. There's nobody will tell us that. So if we have to develop some theory for this, let's also develop some notation. This will be interesting when we try to work out backpropagation. So here, this is just two layers. This is just two layers of connection, and we'll see how this having even one hidden layer can help us solve the XOR problem. We'll in fact take, just for the heck of it, we'll take 4 possible approaches. Right? We'll show that XOR we can solve using all of these approaches. So we have if we have one hidden layer, we have actually no control of how to choose the number of neurons. Here, let's assume there are m of them. And what we have, look at this little animation, is that we have got a different activation function for these. They could be the same, they could be different. It could be hyperbolic time, it could be something like a sigmoid function. Do you know why it's called a sigmoid? All those, if you remember your basic physics, you remember that. See, there are these three distributions. There is the Maxwell-Boltzmann distribution. There's the Bose-Einstein distribution. The only difference between them is 1 over 1 plus e to the power minus, or the plus and the minus signs. Change that, you have two distributions. And when you have the fact that the exponential term is more than 1, then you can approximate it by the exponential term coming to the numerator. That is the Maxwell distribution. So all of these are related. And if you look at the curves of all of these, especially the Maxwell-Boltzmann distribution and the Bose-Einstein distribution, you would have studied this in, let's say, that horrible book on modern physics by Arthur Beezer. You would have struggled through this in our first year physics. So these curves actually look like they're S-shaped curves. S is the closest. See, even the term alphabet has basically come from alpha, beta. It's the Greek alphabet. And the closest character to S in Roman is actually sigma. And there are some other things also. Have you ever wondered that the summation, the notation for a summation is the capital sigma, the Greek character? What happens if the discrete sum tends to get continuous? Becomes an integral. Look at the shape of that integral. S. It's actually a long S. This is no accident, right? So that same philosophical thought actually carries over. So why sigmoid? Sigmoid is something like the absolute strict case of this is when the slope suddenly is like this. That's a unit step function. Okay, it's either 0 or 1. It is continuous at x equal to 0, but it is not differential at x equal to 0 because the left derivative and the right derivative do not coincide. So rather I can model that as a sigmoid, and then I can choose my slope to be as severe as possible and then also end up taking a derivative. So, so now let's look at activation functions. I have about 5 minutes till the break, right? Yeah. Okay. The activation function. So, what was Rosenblatt's model? I would simply take the inputs, I would multiply them by the weights, put it to one compute unit. There could be more than one compute unit. There could be more than one layer for this. So the activation function would be to do this weighted sum and then introduce a possible nonlinearity such that the output is scalar. So this, please note, this is not the most general way to have a nonlinear function. I could have a nonlinear combination of the weights of the inputs, right? I could have x1 square plus x2, and then I could take a nonlinear term there. However, this is restricted nonlinearity, but something which is practically important. If you look at a little bit of history of, see, there are essentially two types of, two flavors of supervised. Of course, there are more flavors of machine learning. There is supervised machine learning, there's unsupervised machine learning. In fact, at IIT Delhi, people think of us teachers being completely superfluous entities because most of what they learn is what students tend to call unsupervised learning, right? We think that we are imparting education, but it's unfortunately not so. There are in general two flavors of supervised learning. What are they? There is regression, which unfortunately people do not talk about much. All of these deep neural networks, the architectures for which they were proposed were all classification problems. But some of them can be used for regression problems also. In regression, the output is one continuous. Okay, it's not a discrete set in terms of whatever outputs are. But classification is only very natural because there are many more classification problems than regression problems. So that's the idea. So in regression, the more typical models for nonlinearity are a bit different. For classification, one often takes a nonlinear function of a linear combination, In regression, one often takes the opposite. It's just that it's a bit more natural for that problem. But all of these are cases of restricted nonlinearity. Alright? Just makes it computationally attractive. What are the transfer functions? Yeah, these are the activation functions. These could be sigmoid, hyperbolic tangent. This is very popular today, the rectified linear unit or ReLU. There are variants of them. One of them called the leaky ReLU. There's something called ELU. Okay. So what is this? This is the sigmoid function, right? This looks like an S. This is hyperbolic tangent. So this is between 0 and 1. This is between -1 and +1. We'll see that the two are related. They are in fact related. So I just wanted to have all of these activation functions in one slide. That's why you see them so small. I'll blow them up later. So this is the familiar rectified linear unit. It's like the characteristics of a diode, right? The piecewise linear characteristics. So it's reverse biased here and forward biased here. So this is the I versus V characteristic. So your independent variable is the voltage across the diode, and your dependent variable is the current which is flowing through the diode. This is the rectified linear unit of the ReLU. This is what is called leaky ReLU. That is, if this is negative, don't take this to be 0, but take it with a slight slope. Okay? And this is what is called the ELU. Okay, so this is the leaky ReLU. This is the definition: max of alpha a comma a, where alpha lies between 0 and 1. And the ELU is actually this. And I'll possibly close this session with a little video. Bollywood. So everybody is asking, ye ilu kya hai? If you've seen this movie, I think this is Saudagar. So everybody is asking, ye ilu kya hai? What is this function ilu? Right up to Dilip Kumar, yeah. See, even Dilip Kumar is asking, what is this ilu? So you'll notice that there's a lot of link between Bollywood and machine learning. And in fact, one of the applications of machine learning today is self-driving cars. Come on, Salman Khan is from Bollywood, right? When we talk about self-driving cars. Okay, so with this little thing, I guess we'll end it here.